In this video tutorial, we will learn how to train YOLOv12 object detection model on a custom dataset. YOLOv12 is the latest state-of-the-art computer vision model architecture. YOLOv12 uses a attention-centric architecture. YOLOv12 can be used for a variety of tasks including object detection, instance segmentation, pose estimation, and image classification. In this video tutorial, we will be fine-tuning YOLOv12 model on a custom dataset for personal protective equipment detection. So let's get started with this. If I have this notebook ready, so I will be explaining the complete process flow. But before we run this script, please make sure that you have selected the runtime as T4 GPU. So Google Colab offers free GPU, so you can use it. So now you can see currently we are using a GPU memory. So first of all, I will install the Ultralytics package. So we will use Ultralytics package to do object detection using YOLOv12. So the package installation will take few seconds. So let's wait for the package installation to get finished. So the Ultralytics package is installed. So now you can see over here, the package installation is done. So I will just clear the output or hide the output. So now I will just import Ultralytics and see if the package installation is successfully completed or not. So you can see that the package installation is successfully done. So now from Ultralytics, I will import YOLO, and then using YOLO, I will load the YOLOv12 model. Plus, I also import image. So we require the image library to display an input or output image in our Google Colab notebook, and we are just setting our current working directory over here. Okay, so to fine tune the YOLOv12 models, in this tutorial we will fine tune the YOLOv12 object detection model on personal protective equipment dataset. So here you can see we have the dataset. So we will fine tune the YOLOv12 object detection model on personal protective equipment dataset. So here we have the dataset. Okay, so we have 3,290 images in our dataset, and we have total 7 classes in our dataset. So this is how our dataset looks like. So our dataset is completely annotated. Okay, so let me just open some other image. So like I think to network the image is completely annotated over here. So the helmet, protective boots, safety gloves as well. So this is the data set we have, and we will using this data set. Okay, so we have 2,311 images in our training data. We have 652 images in our validation data, and we have 327 images in our test data set. And no augmentation is applied on our training data because we have enough number of images in our training data. Usually we apply augmentation on the training data when we don't have enough images in our training data set. Okay, so I will just add the link of this data set into the Google Colab notebook as well. So if you want to download, check this data set, you can just check it by clicking on this link. Okay, so now I will just download this data set from Roboflow into the Google Colab notebook. So if you want to download, export this data set, data set from Roboflow into the Google Colab notebook, what you need to do is you just need to click on download dataset, and you just need to then sign in with your email. Or if you don't have an account on Roboflow, you can just create an account on Roboflow as well. So now I'm just signing in to Roboflow. So after signing, you can just click on download dataset, and you will select the format. So we are fine tuning the YOLOv12 model. So we will select the YOLOv12 as the order format, and I'll just click on show download code over here. Okay, so you can just accept the terms and privacy policy. Okay. Okay, that's good. Let's see. So you can just copy this code from here, and you can just add this code over here. Okay, so you can just add this code over here. So, and if you just run this cell, you will be able to download the dataset from Roboflow into your Google Colab notebook. Okay, So please don't click on restart session immediately. Please wait for the dataset to be extracted completely. So now you can see it's 100%. So now you can click on restart session. If you don't wait for a dataset to be unzipped, then you might not be able to completely unzip the dataset if you just click on restart before the process of that extracting dataset completed. Okay. So now you can see you will just run the cell again. So now over here, you can see we have our data set. So I will just hide the output. So here you can see we have the data.yml file. We have 7 classes in our data set, and C represent the number of classes. We have the class dust mask, eye wear, glove, protective boots, protective helmet, safety vest, shield. So these are the 7 classes, and we have training validation test data set. So we have the images over here, and then we also have the labels over here as well. So like you can see over here. Okay, so in the labels we have the class name, like, and here we have also have the bounding box coordinates. Okay, so this is the class ID over here, and here we have the bounding box coordinate x1 y1 and x2 y2. Okay, so let's see the dataset location from here. Okay, so here you can see in the dataset we have data.yml file, we have the train test validation folders, and we have this .txt file. So okay, so now we will see how we can fine tune the YOLOv12 model on this personal protective equipment dataset. So we need to make few changes in our downloaded dataset. Like you can see here, we just need to make few updates in our downloaded dataset, which we have here, so that we can make it work for YOLOv12. So we will just run the following bash commands, which you can see over here. So this will update the paths. So if you run the bash commands, this will update a training validation and test parts into this data.yml file over here. Okay. So, okay. So now you can see over here. So we have run this command. So this has updated a train validation and test datasets path in our data.yml file. Okay. So So now we are ready to fine tune our YOLOv12 model. So first of all, YOLOv12 comes with 5 different models: YOLOv12 Nano, YOLOv12 Small. So if I just show you all the models that YOLOv12 comes with, so you can just go to YOLOv12 GitHub repository over here. So now you can see these are all the models that YOLOv12 comes with: YOLOv12 Nano, YOLOv12 Small, YOLOv12 Medium, YOLOv12 Large, and YOLOv12 Extra Large. YOLOv12 Nano is the fastest, but it is least accurate, while YOLOv12 Extra Large is the most accurate, but it is less fast as compared to other YOLOv12 models. Okay, so in this tutorial, we will be using YOLOv12 small model. So I will be fine-tuning the YOLO12 small model on personal protective equipment dataset, which I have just showed you here. Okay. So you can use you can use YOLO12 large model or extra large model if you want better accuracy. Okay. So you can just load the YOLO12 small model. So I have already trained the YOLO12, or you can say I have already fine-tuned the YOLO12 small model on the personal protective equipment dataset. So I've done the training or for 50 epochs. So here you can see that the training is completed. So I will not perform the training again because this takes a lot of time. So I will not be repeating this process again. Okay, so over here you can see that the training has been performed, and here you can see we have the mean average precision score with IRU 0.5 and mean average precision score when IRU varies from 0.5 to 0.95, and you can see for all the classes we are getting a good mean average precision score with IRU 0.5 and mean average precision score with IRU 0.5 to 0.95. So we are getting a good mean average precision scores. Okay. So now, after the training completes, in the train 3 folder, we have these different files, like we have the confusion matrix, precision curve, precision recall curve, recall curve. So we have all these matrices available. Okay. So first of all, we can see we have the confusion matrix. Confusion matrix basically tells us how our model handles different classes. Okay. So if you just see over here, like 259 times we are able to detect that there is a dust mask, while 48 times when there is a dust mask our model was unable to detect anything. So out of 259 times the model detected correctly that there is a dust mask, while 48 times when there is a dust mask our model was unable to detect the dust mask, while one time when there is a dust mask our model incorrectly classified it as protective helmet. Okay. So next over here we can see that 497 times when the person was wearing a safety vest, our model detected correctly that the person is wearing a safety vest. While two times when the person is wearing a safety vest, our model incorrectly classified it as a protective helmet. While five times when the person was wearing an eye wear, when the person was wearing a safety vest, our model incorrectly classified it as eye wear. Okay. Similarly, 539 times when the person was wearing a glove, our model correctly classified that the person is wearing a glove, while two times when the person was wearing a glove, our model incorrectly classified it as a safety vest, while one time when the person was wearing a glove, our model incorrectly classified it as a protective helmet, while 89 times when the person was wearing a glove, our model was unable to detect anything. Okay. So this is a normalized confusion matrix. Like 84% of the times, our model was correctly able to classify that the person is wearing a safe dust mask, while 16% of the times when the person was wearing a dust mask, our model was unable to detect anything. Okay. So while only 12%, like only 12% our model, like this is a very low score. So like like 12% of the times when the person was wearing a shield, our model was correctly able to classify that the person is wearing a shield, while 84% times when the person was wearing a shield our model incorrectly classified it as that our model was unable to detect anything when the person was wearing a shield, while 4% of the times when the person was wearing a shield our model incorrectly classified it as a protective helmet. Okay. So this is what confusion matrix tells us. So if we just see over here, with shield, we are just getting a low mean average precision score with IIU 0.5, and with IIUs varies from 0.5 to 0.95. We are also getting a low mean average precision score. So this is clearly evident, uh, like our model was only able to classify correctly shield, or like when the person was wearing a shield, only 12% of the time our model was able to detect correctly that the person is wearing a shield. Okay. So here we have the results of the training. So you can see that the mean average precision score is continuously improving. So if we train the model on high box, there's a chance that our accuracy score will further improve. Okay. So here we have the precision and confidence curve over here, like you can see over here. Let me just uh, so what is basically precision? Precision is basically the simply the true positives out of total detections. So precision is basically the true positives, like how many times the model was able to detect correctly, and out of true positives plus false positives. So you can say that precision is simply true positives out of total detections. Okay. So over here you can see with precision confidence curve. So now you can see that as we increase the confidence score, the precision tends to increase. The precision score tends to increase. The reason is that when we increase the confidence score, we get more accurate uh, detection. Like when we increase the confidence score, our detections might get like we might be able to detect less number of objects So if we increase the confidence score, we might be able to detect a less number of objects, but there will be more accurate detections. So like if you increase the confidence score, there will be less number of detections, but there will be more accurate detections. So you can just remember this, like if you increase the confidence score, there will be less number of detections, but there will be more accurate detections. Okay, because over here, like you can see that when we increase the confidence score, there will be more true positives, there will be less false positives. So the precision score will rise. Okay, so now you can see over here we have the recall score. So like you can see over here, so in the recall score, when the confidence score is low, there will be like if the confidence score is low, there will be more number of detections. But if the confidence score is high, there will be less number of detections. So here you can see that recall is the true positives out of all ground truths. So when if we decrease the confidence score, there will be more number of detections. So there might be more false positives, but is a chance that there will be more true positives as well. Okay, so like in the case of recall score, when that confidence score is low, then the recalls will be high. Okay, because when the confidence score is low, there will be more number of detections, and there is high chance that there can be more true positives. Okay, but here when we increase the confidence score, there will be less number of detections, so there is a chance that some true positives are also missed out. Okay, so here is the model predictions on the training batches, and here are the model predictions on the validation batch. So we have not used the validation images for the training, so it's always better to take a look and see how our model performs on the validation data set. So I have already saved the model weights into my drive, so I will directly download the model weights from my drive into this Google Colab notebook over here. So let's wait. So now you can see that we have downloaded the best model weights from the drive, and you can see here we have the best model weights. So now we'll just validate our fine-tune model over here. So now we are validating our fine-tune model over here. So now you can see over here, we have validated a fine-tune model. Only for the shield class, we are getting a low mean average precision score with IOU 0.5, and with mean average precision score is also low, and the IOU varies from 0.5 to 0.95. So for only the shield class, we are just getting a low mean average precision score with IOU 0.5, and when the IOU varies from 0.5 to 0.95. So now we will be performing inference with the fine-tuned model on the test dataset images. So now we will be testing our fine-tuned model on some test dataset images and see what results do we get. So there are around 322 images in our test dataset, and we are just testing the fine-tuned model on this test dataset images. Okay. So over here, you can see over here, here are the some, I'm just check. So here you can see we have the, like we are uh, just evaluating the performance of the model on the test dataset images. So I've just taken 3 images from 2 to 4. So we are just evaluating the model performance on the test dataset images. So you can see that we are able to detect the protective helmet, eye wear, dust mask, safety vest over here, and a glove. So over here you can see we are also able to detect the dust mask, gloves, safety vest, and here you can see we are also able to detect the protective helmet. So result performance is good on the test dataset images. So now I will just download some videos from a drive into this Google Colab notebook, and I will evaluate the model performance on these videos. So I'm just downloading some videos from the drive into this Google Colab notebook. So just give me a minute. So I will just fix this error. So I have added this piece of code, and now I'm able to download the video from a drive into this Google Colab notebook. So let me download another video from Drive into this Google Colab notebook over here. So I've downloaded the two videos from my Drive into this Google Colab notebook. So I will now test the model performance on these two videos. So the complete video is being divided into 310 frames, and now we are doing detection on each of the frame one by one. Okay. So let's see. So now we are just doing detections on each of the frame one by one. So now here you can see that it's done. So now detection on this input video is done. So now I will just, so over here in the runs detect predict, my output video is being saved. Okay, so if I just see over here, so here you can see we have our output video. So now I will just display this output video into our Google Colab notebook. So this will take few seconds before our output video gets ready. So here you can see we have our output video. So I will just download this video from here and show you on the front screen. Okay. So now you can see over here, we are able to detect the protective helmet, safety vest, protective boot over here. Okay. And the detection results look quite promising, like good results. Okay. So now I will just run the detections on this second video as well. So the complete video is being divided into 267 frames, and we are doing detection on each of the frame one by one. Okay. So that is done. And in the runs detect predict folder, we have our output video being. So here you can see we have our output video as well. So let me display this output video into our Google Colab notebook. So now you can see that the complete video was divided into 267 frames, and we are doing detections on each of the frame one by one. So now an output video will be ready in few seconds. So let's wait for it to get completed, and then I will show you the out results over here as well. So now you can see currently it's processing. So now you can see our output video is ready. So I'll just download it. So now you can see over here, we are able to detect the safety vest, protective boots as well. So the detection results look good. Okay, so you can also fine tune this model on higher epochs as well. So in this tutorial, we have seen that how we can fine tune YOLOv12 object detection model on any custom data set. So that's all from this tutorial. Thank you for watching.